Let's talk about transformation. As a warm-up, we can think of transformation as transportation from the original green location to the red destination. The original location, the original vector space, the original green world is defined by its basis, green basis, B1, B2 vectors up to Bn, where n is the dimension of the green vector space. So it means that any vector that belongs to this original vector space might be presented as a linear combination of the green bases with particular weights, C1, C2, and so on up to Cn. We can organize all these weights and put them into column and call them coordinates and call this coordinate vector. And we have equal sign because this notation, alternative notation, is equivalent the linear combination we have on the left. So this vector column, vector of the coordinates, it means exactly the same. It means that vector v might be presented as a linear combination of the basis vectors b1, b2, up to bn with specific weights c1, c2, cn, c1, c2, and up to cn. Okay, so what next? Next, we need to emphasize that transformation that is not just in general, that is not just about moving some guys from original location to some new destination, from green point A to red point B. So transformation also in general transforms, changes this original vector somehow. So transformation T applied to vector V from the original green space, green world, it will change this vector to some kind of a new vector, T of V. It will be in general new vector. And this new vector will belong to the new world, to the new red vector space. And as a citizen of this new red world, this vector T of V must be presented as a linear combination of the red basis vectors, B1, B2, and so on up to Bm, where m is the dimension of this new red vector space, new red world. Again, and alternatively, we can collect and organize all these weights, the red C1, C2 up to Cm, into a column and call them coordinates and call this column coordinate vector. And this is equivalent representation. So this column means exactly the same as this linear combination on the left. This column means that vector T of V might be presented as a linear combination of the red basis vectors B1, B2 up to Bm with these specific particular weights, coordinates C1, C2 up to Cm. And of course, also we may think of the transformation as a special kind of a function that takes the green coordinates of the vector v that belongs to the original green space and takes this column of the coordinates as an input and produces red output, red coordinates of the T of V vector. Okay, so now we're going to try to prove an important theorem. In general, we're going to go abstract and prove a theorem. Let's start with applying the linear transformation to the vector v, arbitrary vector v, from the original location, original vector space, the green world. Let's apply the linear transformation to this vector and apply the transformation to the left side of this equation, to the linear combination of the basis vectors. Then we're going to use the properties of linear transformation. There are two of them. The first property states we can distribute linear transformation onto all the terms, onto all the individual vectors in this linear combination. That's what was done on this step. And the second property allows us to factor out all these coefficients, C1, C2, and so on up to Cn, out of the linear transformation. Next question, we need to comprehend what is the outcome after applying transformation to basis vector 1, basis vector 2, and all the green basis vectors up to Bn. So what is that? And we need to realize that transformation T, it changes all the vectors from the original green world into citizens of the new red destination, of the new red vector space. So T of B1, for example, that a new vector that will belong to the new red vector space. Therefore, it might be presented as a linear combination of the red basis vectors with the specific coefficients alpha. And as we did before, we can use coordinate representation of this statement. So we can organize all the alpha coefficients and call them coordinates into a column vector, which means basically the same exactly as this linear combination. It means vector T of B1, it belongs to the new red world, red vector space. It might be presented as a linear combination of the red bases, and those weights, we're going to call them coordinates, and we're going to organize them as a column vector. So then we're going to do, we can do the same, we can say the same, state the same about T of B2, T applied to the green basis vector B2. We're going to end up in the red destination space, and we're going to state that it is possible in general to represent this vector T of B2 as a linear combination of the red basis vectors. And those coordinates in this column vector represents the weights accordingly. And what? And so on. And we can say that, state that for all and each of the green basis vectors and outcomes out of the applying the transformation to all the basis vectors in the original green vector space. Okay, so now let's just plug in. Let's just plug in T of B1, T of B2, and so on, T of Bn. Let's just plug in what we have. Let's use the coordinate notation, those column vectors. Okay, so let's plug in. And the last equation, mostly green, turns red, mostly red. Okay, so C1 times T of B1. What's T of B1 one more time? That's the column vector on the right with the red coordinates of this vector T of B1 in terms of, in the language of the red destination. Okay, and T of B2, it's equal to this column, and so on. T of Bn, it's equal to this column. We also substituted on the left T of V. T of V, that's what we did previously, with the equivalent notation, with the coordinates and weights C1, C2, Cm organized as a column vector. So this is the equation which is equivalent to the equation above. And this is a vector equation. This is a vector equation. We have column vectors and some green coefficients, C1, C2, and Cn. Okay, the very last step and the most important step, sometimes it's called aggregation. So how it works first? We are going to aggregate all these vectors into the columns of this matrix. So the first vector constitutes the first column of the matrix. The second vector turns into the second column, and so on. The last vector gives us the last column of the matrix. This matrix is called, by the way, matrix of the transformation. Matrix of the transformation. Let's figure out first, let's clarify why this vector equation is equivalent to this matrix equation. There are a few ways to prove it. One way is you may pick any entry on the left, C2 for example, and calculate it 2 times using this vector equation and then using this matrix equation to make sure they are equal, identical. So let's do it really fast. C2 in red is equal to the green C1 times alpha 2,1 plus green C2 times alpha 2,2 plus and so on plus Cn times alpha 2n. That is what we get from the vector equation. Now, matrix equation, C2, how we calculate C2? That's an element in the second row and the first and only one column. Second row, first column. So we're gonna multiply second row of the matrix times the first and only one column. The second row times the column. A21 times C1. A21 times C1 plus alpha 22 times C2, alpha 22, C2, and so on, alpha 2n times C2, alpha 2n times the last element in the column, Cn, alpha 2n times Cn. As we can see, indeed, the outcome is the same. The alternative way is to use so-called column view on the matrix multiplication. That is something we were struggling a bit in one of the previous projects. So what column view of the matrix multiplication gives us? So this matrix times this column is equal to the first column times the first weight, C1. The first column times the first weight, plus the second column times the second weight. And it's here, plus and so on, plus the last column times the last weight. And it is here. So anyway, those equations, the vector equation on the top and the matrix equation below, they are equivalent. And this is the outcome. This is it. This is the outcome of the whole consideration of the theorem. So, and it says that we have a matrix of transformation, and we can take the green coordinates of any vector v as an input, and then perform multiplication. This matrix times this column, it gives us the outcome, the red outcome, the coordinates in the new destination, red world vector space for the vector t of v, for the outcome of the transformation. Okay, and this procedure turns out to be really powerful, and we're gonna apply this procedure in many cases for many applications and problems. So what is this procedure? One more time, it works just like that. When we deal with the transformation in two linear spaces, two worlds, the starting location, green world, and the destination, the red vector space, red world. So we need to start, we always start with the consideration how this transformation affects, influences the basis vectors of the original green vector space. We apply this transformation, whatever it is, we are doing abstract proof. We are not given the exact parameters of this transformation. Whatever it is, it will be given in a particular problem. So apply this transformation to all the basis vectors, the green basis vectors. Figure out the red outcomes, the coordinates of this vector in the new red vector space. Then collect all these columns and aggregate them into matrix of the transformation, and you're done. Then you can use this formula. Then you can apply this matrix of the transformation to the green input of the coordinates and get the outcome, the red coordinates of this T of V vector, which belongs to the new red vector space, the destination vector space. That's how it works. The theorem has been proved.